So hello and welcome, everyone. Nice to see in such numbers. I'm Lukas Kekeli. I'm the CTO of DYNANIC company, and today here with me is Lukas Shishmish, our developer. And today's webinar will be about delivering next-level acceleration to network security, especially about IDS Suricata and some options how to accelerate this kind of workload or this kind of application using FPGAs and using high-speed network links. So allow me to welcome you again. The presentation will be recorded and every participant will be able to download the recording afterwards. If you have some questions, you can navigate at the right bottom corner of the window. There should be an option to write a question. So I will be collecting questions throughout the presentation. And at the end of the presentation, we will go back to the questions. So feel free to write your questions during the presentation. At the end, we will answer them. So let us start today's webinar, today's presentation. I would like to start with a bit of introduction of our company. So we are DYNANIC company. We focus on FPGA and high-speed networking, development of high-speed network acceleration. We are based on 2 decades of research, backed in Czech Republic, backed by university, backed by research organizations, and we are currently partners with major FPGA vendors and major vendors of FPGA boards. So our expertise is FPGAs, and we want to allow other users, other network providers to be able to utilize the benefits of FPGA technology with our main flagship product. Our product is called DYNANIC, and it is a complete packet processing pipeline for FPGA cards. We support cards from many vendors with the same functionality, and we can scale up to 400 gigabits with current FPGAs and even further with future FPGAs. All of this comes with a unified standard API based on DPDK, which is open sourced, and so you can offload easily some critical parts of your application or of your network processing into the prepared FPGA firmware. So we take care of the whole firmware, we take care of the hard part, the programming of the FPGA, and our customers or you can focus on your added value on the software level. So this is our product, and here today we are with Lukas Shishmish. So let me introduce our today's speaker. Lukas Shishmish is a senior software engineer. He's working at DYNANIC right now. Before, he was a researcher at CESNET and University of Technology in Brno. And he's also one of the core developers of Suricata IDS, Intrusion Detection System, which is an open source tool for providing some kind of cybersecurity or from the area of cybersecurity. So he's focusing on network-based intrusion detection, mainly with Suricata. He is active part in the open source community around DPDK, and he promotes utilization of IDS and similar system in cybersecurity area. So his presentation today will be about this topic. So with this, Lukas, you have the floor.
Okay, thank you so much, Lukas, for a nice introduction. Let's have a quick overview what's ahead of us today. And we will quickly recap what's the role of network security applications in today's networks and environments. Then we will go over what are the actual performance bottlenecks in IDS solutions, and we will try to address them in the next steps. So we will try to address how we can maximize the processing efficiency with DYNANIC and FPGAs, how we can handle encrypted traffic, because that's still a big topic today, and how we can further improve the basically processing in IDS and other workloads with pattern matching engine that's built in the DYNANIC FPGA card. Okay, so let's proceed. About the current role of network security applications, I wanted to give a quick recap how we can basically secure current environments. That basically corporate environments can be secured either with endpoint detection and protection systems and with network analyzing applications. What are the common network security applications? Just so we have some overview, it can be just high-level network monitoring applications. Maybe you've heard of Scrutinizer or NTOP or IPFix Probe. For sure, you've heard of firewalls. That's examples such as OpenSense, Fortinet, or Network Firewall. Or there are, as mentioned, already network intrusion detection and prevention applications that receive the traffic and try to look for malware in the traffic. With the last point here, I'm asking if the network security applications are even necessary at this point, because I've heard that from some colleagues that, okay, we have endpoint protection, we can install it on all machines, and we don't really even need network security applications. But that's not entirely true. Network security applications are still needed and still very useful, and will continue to be very useful in the future decades as well. So why do we need the network security applications? I've kind of listed the main arguments why should we use it, and that is for visibility and auditability. So while endpoint protection system can basically access the decrypted traffic, access the system information and resources, it's all nice, but if sometimes we cannot basically install endpoint protection on all devices. We cannot install it on IoT systems. We cannot install it on third-party managed devices, routers, etc. And if somebody comes to our corporate office and plugs in some malicious device, we of course will not have any endpoint protection installed there as well. So that's why we still need to deploy the network security applications to give us the visibility into the network, who communicates with whom. Then it's also very useful that these applications are device agnostic. So anybody who is communicating follows some standards, which network security applications understand, and we basically all have logs about these communications without any pre-configuration beforehand. They also provide us auditability, meaning you have the answers. Did somebody contact this website freerumupgrade.com in the last 9 months? It's all basically in the logs of network security applications, which you might not have with the endpoint protection. So yes, it's still very useful to have them. On this slide, I have a little diagram of the common network security applications. Down on the bottom of the slide, we have the diagram of the network topology, where we have, let's say, firewall as one example of the applications. That is basically the controlling applications or the guarding applications that inspects just the packet headers and controls what's coming in and out due to some network policies. Below we have network monitor, which is the high level just collecting application that collects informations about the flows, who communicates with who. It can detect bottlenecks, downtime, and some anomalies as well. But both of these applications are pretty lightweight. They only inspect the packet headers, whereas the intrusion detection and prevention systems, depending on how they are configured, go a bit further. They are deep packet inspection applications, so they detect malware, or they basically do the detection in the payloads of the packets. They reassemble the traffic and much more. They can, of course, work as the more basic firewall or network monitor applications, but they are really they are really aiming on more advanced use cases. As a basically example of intrusion detection and prevention system, we chose for this presentation Suricata, of course, which has the two inputs, and that is traffic, of course, from the left. From the top, we have security rules. So IDS works with some pre-written security rules by security researchers, who basically write these signatures to or rules to detect malware or policy violations. On the right, we have the output, what's coming out of Suricata, and that's the detection alerts. If something bad is basically happening, then we know because of Suricata. Then, of course, it's the flow information as the flow monitors or network monitors, as previously mentioned. Then the application layer metadata, that's the advanced level of metadata that IDS can provide. File extractions for auditability, it can extract, let's say, the email files and etc. Why we also picked Suricata is because it's open source, of course, system, but it's heavily used in major organizations around the globe. And of course, it has its high performance threat detection engine. It's actually the fastest threat detection engine out there, especially from the open source ones. It's very scalable. It's quite common to see even 100 gigabits of deployments in Suricata. And of course, it provides robust and flexible rule language. So the security researchers who research the malware can write what they need in the rule language. And based on that, Suricata then detects the threats in the traffic. It has also very good integrations with other security tools. The outputs are in JSON, so you can pick the CM of your system of your choice and feed it with Suricata data. Okay, that's all nice. So that's all kind of the benefits of Suricata, but what are the, let's say, the downsides? People often mention the false positives, alert fatigue, so being overloaded with the output from Suricata. Sometimes it's the configuration complexity. So Suricata has a lot of options to configure, but with a bit of training, you can cover all of these. Especially the alert fatigue is something you need to tune the alerts or the detection rules to your environment, and then the alerts will be decreased. But what DYNANIC can help you with is the high resource consumption, because generally you need per 500 megabits of traffic, you need one CPU core, which sometimes when you scale up to 100 gigabits, it can be quite a bit. This number is just a rough estimate. In some networks, it might be even 1 gigabit, but 500 megabits is a good estimate. And when we looked at how Suricata IDS can be improved and how we can reduce the resource consumption, we basically have two options, and that is either optimize the internal processing. So yeah, we use, let's say, better data structures or faster algorithms in Suricata, but it's not always easy. Like if it would be that easy, we would probably use that already. But we can also leverage some metadata embedded in packets. That's generally not available, but as we will see later on, DYNANIC can provide it. Or we can, the other approach how we can accelerate Suricata is to reduce the amount of processed traffic. So let's say we can filter out the heavy flows such as data backups, video streaming services such as Netflix, YouTube, etc. Or we can filter out encrypted data, basically TLS, HTTPS traffic, because Suricata or other network applications cannot really decrypt the data unless proxy, decryption proxy is configured. And here we are on the overview how DYNANIC can help, let's say, Suricata IDS and similar applications to process more traffic. Of course, it starts with the optimizations of the internal processing, meaning we will use DPDK to achieve higher speeds. Then, as mentioned before, it can execute some, let's say, pattern matching operation in the DYNANIC that can provide metadata to Suricata. And based on that, we can save some CPU cycles. Another approach is by reducing the amount of process network data. So the packet classification framework in the DYNANIC can help us with that by filtering down the data that Suricata doesn't need to or doesn't want to see anymore. Okay, so in the next slides, we will kind of go over these examples that I mentioned in the previous slide. So I think, yeah, we both of us, both with Lukasz, we mentioned standard processing and DPDK processing, like what's the difference? So just so we are all on the same page, DPDK is different because, as we can see in the diagram on the right, if the packet comes to the standard processing, it goes through kernel, and then it goes to the virtual machine where our, let's say, application runs. But the kernel adds up quite a bit of overhead. So what DPDK does is that it provides some abstraction layer above the interface card, and that basically the application can access directly the interface. This is not DYNANIC specific. Basically, with DPDK, you can use any interface you want to use, but DYNANIC also supports this. And I was actually implementing DPDK into Suricata, and in Suricon 2021, I actually showed that it brings at least 10% of throughput. So that's something you can gain basically for free just by switching the different capture layer. Other approaches how we can accelerate Suricata is by reducing the traffic that it inspects. Of course, the main part, as mentioned before, is the encrypted traffic. Suricata cannot decrypt the traffic, so why should we even bother inspecting the HTTPS traffic, for instance? The usual port for this is 443, so we can block basically the whole communication on the port 443 and we are done. That is not completely true because we still want to care about at least the let's say TLS handshakes. TLS is the encrypted communication when the communication starts. The handshake is actually unencrypted. So it's very favorable for Suricata to see this handshake and detect based on that. The most common are, of course, the JA3 or JA3 server or JA4 fingerprints. Based on that, you can see what is the application that starts the communication, or what is the application that responds to your handshake. Then, it's, of course, in the handshakes, there are some other information, such as server name identification that you can detect on. But what we've seen is that majority of traffic is encrypted. So what we kind of need is something that just give us the handshake only to Suricata, and then Suricata processes that, and like it's not for Suricata, it's not interested anymore the rest of the flow. And this is something we've done before we took some samples from academic networks and from commercial networks, and on the left graph, we basically see that what is in blue is the encrypted part. So in the current network, on a backbone network, you see that 80% of traffic is actually encrypted. But as I mentioned in the previous slide, we still want to see a little bit of those 80%. And how much we want to see, we see actually on the graph on the right. Yes. And that is this handshake. As you can see, the handshake only is only like 2%. So out of these 80%, we want to see only those 2%. After that, it's basically something that it's not very much interested for Suricata. And when we also evaluated how long these flows are, we actually seen that 98% of TLS flows are less than 1 megabyte, which is pretty short. So something that you need is it's very like a very active filtering mechanism, which is very fast. It can basically filter out on after a few packets, and of course that gave us good motivation why we should implement that in the FPGA. This is basically the high-level diagram. The traffic comes in, the FPGA card, the DYNANIC, processes the traffic based on its internal connection tracking table. It evaluates whether the traffic should be bypassed or not, and then if it should be passed to Suricata, it is. As I mentioned, it's stateful, so we basically consider the state of the connection before making the decision to bypass or not. Again, here is some more in-depth, but still pretty high-level diagram of how it works. Is that the traffic comes into the DYNANIC based on the traffic that the FPGA card sees. It's parsed by the header field extractors. Then it's passed to the TLS prefilter, which evaluates the connection, whether it should be bypassed or not. It also basically takes information from the flow context, so from the connection tracking table. What's the state? I said before it's a stateful bypass. It's because we first want to see encrypted connection from one side of the flow, and then when the other side of the communication replies, when the client, let's say, replies with "Okay, let's encrypt this connection," then we can bypass this connection, and we can track that this connection is bypassed in the connection tracking table. The ultimate or final decision whether the flow should be bypassed or not is in drop FIFO, where the decision is taken and the packet is either dropped or passed through DMA to Suricata. Here we have some overview how it actually helped us to accelerate Suricata. We have two scenarios. One is IDS controlled bypass, and then the other is DYNANIC TLS bypass. On the left, we have the 100% of input traffic, basically, and it goes through the interface, and basically in Suricata can also support something like this, let's say the encrypted bypass, but because of its stricter mechanism, it only bypassed let's say 9% of the traffic, which wasn't really much. as we have seen before, the traffic had nearly 80% of encrypted traffic. In the dynamic TLS bypass, the 100% is again the input traffic. Then it's processed by the FPGA, and what is delivered to Suricata is only 58% of the originating traffic, which is still not 20%, but we still we are better safe than sorry, right? So we still rather inspect a little bit more traffic and are actually very careful about the stateful bypass. But what was interesting about this is that even though the original bypass only bypassed 9%, it actually led to speed up of 13% in Suricata. So Suricata could process 13% more packets. However, in a dynamic TLS bypass, it could process nearly 80% more traffic. So that's a huge win for dynamic. To wrap it up, this part of acceleration, the TLS pre-filter engine bypasses the encrypted traffic. It's the stateful TLS pre-filtration in place. It's directly on the FPGA, and FPGA directly, the dynamic directly decides whether to bypass the flow or not. And you can see basically the increase in throughput by over nearly 80%. I also mentioned this last point, which is the reduction of false positives. As you've seen before, the Suricata seen encrypted traffic before in a much larger volume, and that led to some false positives because it was, let's say, searching for patterns in encrypted data which didn't make sense. So by filtering out the noise and focusing on what's important, we were able to even decrease the false positives from Suricata. Now, when we had this kind of settled, we were kind of thinking, what can we maybe accelerate more in Suricata? So we did a heat map profiling of Suricata. There are some interesting data from this, but I will highlight the detection part, which takes nearly 60%, out of which the packet payload pattern matching takes nearly 35%. That's quite a bit, and that's something that Dynanic can also do because it has the pattern matching unit directly on the FPGA. So some quick recap. What the pattern matching engine on Dynanic can do. Dynanic has a pattern table which is filled with hashes of the patterns that we want to search for, and then as we have an input stream in the FPGA, we hash it 1 byte by 1 byte, and then compare it with the pattern table. And if it matches, then it means that we very likely found the pattern. I say very likely because it's a hash, and sometimes there might be, let's say, collisions. But what is good and what's good thing about this is it's better for Dynanic to rather flag it as let's say pattern match than miss something and say that it didn't miss anything. So that's why we call it pre-filter, because even though it's fairly precise, it's not 100% precise. But what is good thing about this, it can scale up to 400 gigabits of throughput. And depending on how big the pattern table and how big throughput you want, we can configure it. This also has a support for regular expressions, which will convert the regular expression into the pattern table, and based on it, we can find patterns in the input data stream. So how it basically works with Suricata. Suricata receives some set of rules as an input. Suricata parses these rules, extracts the patterns that it needs to search, and then pushes it into DYNANIC. DYNANIC is initialized, and when it's running, DYNANIC can add metadata to this packet that, okay, some patterns are found, and let's say also the IDs of the actual patterns. So later on, Suricata can really verify if it found something or not. Here we have it in the diagram. So in the initial configuration, we have Suricata rules, which are passed to Suricata. Suricata parses those rules, extracts the patterns, and then the patterns are loaded into DYNANIC. DYNANIC searches for those patterns. In the data processing step, we have a raw packet. And when the packet is transferred to Suricata, it's kind of metadata enriched, as it's here is called. So by metadata enriched, I mean the packet has information what patterns basically matched in this packet. After we've done the evaluation, we basically seen that we see the improvement by around 40%. This can be, again, a little bit dependent on the traffic that you have in your environment. But if you have more unencrypted traffic, it can be even more. If you have maybe less, and it can be a little less, but 30 to 40% of increase is very highly expected. And considering it's directly, the pattern matching is directly in line of the data path, you can see that the scaling is not really problematic, and it can scale to 400 gigabits, as mentioned before. Okay, so with this, I would like to give a quick recap. What can DYNANIC basically offer? And that is DPDK support for your applications, the TLS pre-filter engine if the application is not really a fan of encrypted traffic, it can use the TLS pre-filter to reduce the amount of traffic it needs to process. And then it's the pattern matching engine to provide what patterns matched in the packet payload. And with all these features, you can improve the application performance, so meaning you will increase the throughput, or you can save cost by reducing the number of CPUs that you need to process your current traffic. With this, I would like to conclude. Thank you for staying with me, and I'm ready for your questions.
Thank you, Lukasz, for a very nice presentation. Looking into the chat, I see multiple questions, so maybe you can start from the first one. So the first question is there an alternative to Suricata with similar or better features?
Yes. So there are some alternatives, some, let's say, let's call it private alternatives. So you can have some Palo Alto solutions, or another very popular IDS solution is Snort. It's made by Cisco, and it's basically integrated in Cisco products. Suricata is more open source, and you can find Suricata actually in other products, let's say from CoreLight, from Stamos Networks, from Amazon, where they don't even basically tell you that you are working with Suricata, but you are actually working with Suricata. Suricata is in the backend, and they provide you the front end. So depending on what you want to use, you have the options.
And maybe if you can tell more about the features, are there some highlights like Suricata is the best in something, or?
Right. Well, Suricata is with regards to performance, is the highest. It's like basically better than Snort. We don't really have access to, let's say, Palo Alto intrusion detection system, so we can't really evaluate that. But with regards to also other features like detection features, it's, yeah, I basically don't feel like there is very much missing for the network um, researchers, and for our network administrators, we basically within the team we try to help them as much as we can. What I can highlight is Suricata highly community support. So there is Discord channel, there is forum where you have problems, you just ask and you get responses.
Okay, I think this was very nice answer. If the author of the question have some further sub questions, feel free to continue writing your new questions or sub questions into the call. So as we will go through other questions, we can get back and maybe give you a more advanced answer. So continuing with the next question, is this acceleration dynamic specific, or can I use it with other platforms? This is from 1619. So I think somewhere in the beginning of the presentation, you have a slide with basically highlighting what kind of accelerations are you using.
Right. So yes, with DPDK, yeah, you can use any interface you want. From my experience, the NVIDIA interface cards are have basically a good support in DPDK. You can also use Intel cards, but as mentioned, NVIDIA has better support for DPDK. Then the pattern matching operation, it's basically dynamic specific, and Suricata controlled bypass, you can find that in other NICs possibly, and it will be soon pretty new feature open sourced within DPDK. So you will be able to use that with other cards as well. But so far it's dynamic specific.
Yeah, I think you mentioned on some later slides that even with DPDK, you can save up to 10%. So this should be applicable for any platform, I assume.
Yeah.
But of course, there are some dynamic specific features that you mentioned here in the presentation. Okay, going to the next question. If provided keys, I assume, can Suricata decrypt? So I think the question was during the slide when you were speaking about the TLS and how we cannot decrypt the traffic. So I assume the question is, is there a way how to provide keys to Suricata to be able to decrypt the traffic?
No, Suricata is usually in these scenarios, if you have the keys, it's usually configured with other software. If I recall correctly, it's called Polar Proxy, which basically decrypts the traffic for you, and then this traffic is routed to Suricata. So yeah, it's also used, especially in corporate environments where you have ability to control what are the keys and how you want to decrypt the traffic.
Okay. Another question is, does the 80% acceleration hold or is even applicable for other applications or use cases?
Well, I believe
I think it was about this slide. I think yes.
Yeah, the bottom right corner says that it's speed up 80%. I believe it is. So it depends what application you have in mind, but basically any application that is not interested in encrypted traffic can benefit from this. So of course it depends. It depends how your application goes deep into the traffic or how much time it spends on the packet. But basically, the more it spends on the packet, the bigger increase in performance you can see with the TLS bypass.
Yeah. I assume, again, as you said before, even just simply using DPDK can save you some percentage. Adding some, in this example, this is Suricata specific. but adding some kind of acceleration or bypass can save you additional percentage of performance. Here you have it specific for Suricata. I think similar can be done for other IDSs, but in other use cases, I would assume that similar bypass can be configured and similar performance update or performance gains can be achieved. But as you said,
Yeah.
it really depends on the application.
Maybe it's a good addition to this that okay, TLS bypass is one thing, but if you have some traffic in mind that you want to bypass, DYNANIC has packet classifiers on FPGA, so you can basically push some rules into the DYNANIC, which will match on the traffic. And if the traffic is matched, then it's and then it is bypassed. It can be either at runtime or during the initial configuration. So depends on your application.
Okay, and the last question, Suricata support pattern in other NICs. So I think this was somewhere at the end of the presentation when you were speaking about the pattern matching.
Yes.
So can
sorry, I misheard the question that you just read.
Yeah, I assume the question is if Suricata can offload or accelerate pattern matching into other NICs. I think on a different slide you had some schematics where you showed like Suricata will parse the rules, and upload them to the NIC. So is this DYNANIC specific, or are there other NICs that can do pattern acceleration?
So this is basically DYNANIC specific. I don't know any other card that is FPGA card and has pattern matching on it. So this is pretty much DYNANIC specific. What I can mention is the NVIDIA Bluefield cards, which they have the pattern matching engine on the SmartNIC, but it's not in the data path. So you need to first transfer packets to Suricata and then back to the network interface card and then get back the results. And yeah, this support is not yet merged in Suricata.
Okay, understandable. So that's were all the questions. Thank you all for participation. Thank you, Lucas, for a nice presentation and nice discussion afterwards.
Thank you all.
That's all from us. That's all from this webinar. So once again, thank you for your time and for your participation with very nice questions. And we'll see you on the next webinar.
Okay, thank you so much, everyone. See you.
Bye, everyone.
Bye-bye.